Yeah, I was watching a video and a guy's describing his new idea for a space elevator.
That one
Yeah.
again.
Yeah, except it's always the same problem. It's the weight of the structure that's going to take the thing up there and how to keep it in place and all of the regular nonsense. It is simply a physical impossibility because our weather system's going to take the thing out when you start building it. It's like building the Tower of Babel, I would think.
Is a bit just like that. Oh well,
Yeah.
such is life. So, what was your view of the chat with Wheezy on Saturday?
Oh, it was really good, actually. I was going to go over a couple of things on the rover because there was quite a few comments about asking about the rover. The number one thing is, some people have the impression it was just made out of a Jeep or something like that.
How many times I've shown that rover being folded up and manufactured and tested, they still claim that.
Yeah, I know.
The biggest thing is when they decided to put a rover into service, it was very late in the game, probably late 67, early 68 when they decided to do that. So the first renditions, their first training machines, did not fold up. They were just an aluminum frame. They had rubber tires and they had gas motors. And then when they first started testing the electric motors, they just put rear wheel drive on their trainers out there, didn't have four wheel steering or anything else like that. Those were the first trainers. And of course, there's many other renditions of it that they simply put together to put into Santa Claus parades and stuff like that you see, right?
Yeah.
The dimensions of the vehicle is very close to a Willys Jeep, like a Second World War Jeep. That's the seating position and the tire position. Well, that's the human body. Your seating position, your steering wheel, console, everything else there, your tires are going to be there. That's how a Willys Jeep was made. So it does match those dimensions, but it had to fold in. The main body of the vehicle is basically a 60-inch square, 5 feet by 5 feet. And that had to fit into the LEM, into one of the quadrants. That's the initial design. So the rest of the vehicle had to fold up. So the front end folds up and over and back, and the wheels are disconnected and then flip over. They flip the other way in. And to make them fit in there, the fenders that they put on there had to retract as well. So that you had the front and the rear fender, they slid up on slides. They were just made out of fiberglass on the thing to fit in. And the fenders also had to be attached to the rear of the hub on the vehicle so that it went with it when it folded up. That had to be in there. That also had to have enough space when they designed the electric motor as it folded over, because it's in there too. It had to fold down, everything had to fold down properly into that. So when the front folded up, the batteries couldn't be there at the time. The steering linkages and everything else all had to be connected when it was opened back up again. You'll never see that in a video of them doing the LEM. You'll never see them putting the batteries on. Funny, when you look up the specifications on there were 29 volt batteries that were in there. Why they come up with 29 and not 30, because it's 6, 6, 6, 6, right? It's 6, 12, 18, 24, 30. They come up, have to be 29 volt batteries, except the electric motors are actually 36 volts, and that's stated in PDF files.
Right? Well, NASA has rocks that you step on, or they have rocks that you run over, and they just flatten out. So maybe someone stepped on a battery that fell on the floor and they stepped on it, and now you have half a battery. So now you have half of 1.5 volts.
Right. So that's the same as Shatner when he leans into the rock in a cave and it gives away, right? And you see the hand push a piece of styrofoam rock at him, stuff like that. Anyway, I'll just share the screen a little bit here so we can have a little better look at what we're talking about here on this rover. And there are several updated documents on this machine. People need to understand that. Here's the basic. It folds from here. There's a bar across, and this folds up and over and stops just short of the console there. This piece folds up and over, and then the wheels simply flip in. The electric motors, everything else are there. The steering has to be disconnected for that to do that. You'll never see these astronauts connect any of this stuff. They either would have had to turn it up on its side, to make the connection, or they'd have to do it while it was still suspended when they first start to open it and it's still up in the air.
Yeah, you don't see that on Apollo 15, and they show the whole thing.
That's right. So the entire vehicle, Earth weight, of course, is 462 pounds. That includes the batteries, everything. And so they call the equipment. Without the batteries, for them to be able to flip it up and make the connection, this would be very lightweight, because the battery are almost half the weight of this vehicle at this point. These were like 75 kilo batteries, so they're like basically 150 pounds a piece in that range that we're on here. The batteries themselves, if you read the PDF files, were one battery was designed to run the front two motors and the other battery was designed to run the rear two motors. However, they could be switched over if one battery fails to run all four motors if they wish. And that's the same as the steering. Four-wheel steering on it, you could disconnect the four-wheel steering and set and lock in the wheels straight, either on the front and or the back, either which failed. And of course, in Apollo 15, one of the batteries had failed, and they don't show you making any of the adjustments to work on that. The steering also failed, where they had rear wheel steering only, which means they would have had to get in and under the vehicle to disconnect the steering because it had failed and lock the front wheels straight. And if you listen to Roger Stone, his presentation at the BIS, he simply said they parked it in the shade overnight and everything was working fine. So I don't know if parking it in the shade regenerated the battery or not, because it didn't seem to lose any distance on the thing. Yeah. When you come up on the console here, there's actually a mistake right here. This is the sun shadow device, and it works with this dial here. This is not a compass, and there are articles out there saying that this was a compass, which means you'd have to have, a magnetic field around the moon, the same as we do the Earth. What it actually works at, there are some other documents out here, not this, like this is one of the updated ones showing a mistake here. The dial actually lifted up off the console so that it's level, and it had a post in the middle that went up like a sundial. They call it the sun shadow device. And because the sun is coming in from the east, either within a few degrees, NASA could tell them the exact degrees if they want. But what you do is you turn the dial around so that the shadow is over the west, because the sun's coming from the east. And that gives you your north, south, east, west direction on it. And the other mistake they made with it is they have this bearing, distance, and range in here. And you'll see updated PDF files claiming that the distance is from the LEM, and that as it's coming back, it recalculates using a computer and displays it on this dial up here. Well, this dial is a cable-driven, mechanical gear-driven. They're cable gear-driven device. So as you're traveling forward, it will show you your distance. You can't run it backwards. You can't alter it. You can't do anything to it. And all of these three gauges are the same way. They claim that they added a computer, and the computer takes the average of the four wheels, the rotation of the four wheels. That gives you your speed. And then the computer can calculate how the wheels are turned, and that gives you your bearing on the thing. And that has to be through the four-wheel steering as well. It becomes quite complicated to do, even in today's age. And you'd need a computer the size of a house to do that.
You would, yeah.
And they claim that the computer is just located underneath the front frame at the very front of the vehicle, which there's nothing there. It also has one on the harmonic drive gear reduction unit, which is just a torque multiplier. It's like low range on a four-wheel drive vehicle, except the harmonic drive is just a little different design. Anybody that's interested in looking it up, you can look it up and see it. It reduces the speed of the electric motor by a factor of 80 to 1. So it doesn't have gears in it as like a standard transmission. It's just an 80 to 1 reduction gear. Right. And it has to be lubricated. A standard vehicle uses like 75, 90 gear oil right in it, except you'll find that because it's NASA, they use a 72 weight. And you'll see right here, here's a 36 volt motor on the thing. And it automatically shuts off if it hits 400 degrees Fahrenheit. All of those things are on the rover. Any shot that we have, any of the photographs that are of the rover, of course, show the wire wheels. The wire wheels were one of the longest things it took to develop, and that was done by, well, General Motors, and Goodyear was building the tires out, the specifications for the tires on there. So they were kind of working jointly together to get the vehicle ready with all the specifications. Now, the wheels themselves are a one-piece unit. The hub and the tire, if you want to call it a tire, is all one piece. So they created the rim, and then they put titanium hoops all the way around it. And you'll see that in the photographs. You can see right through the wheel itself. They're titanium hoops. Now, they couldn't weld titanium then. It didn't learn how to weld titanium until you get into the 1974 or something, when they started to learn how to do it. So that you'll see the rivets in the wheel hub where they riveted them on. Then they put the wire mesh over top of that. And then they put the chevron tread pattern on there. Those are also titanium on there, and they are riveted on. And you can see that they're riveted on. That is the only spot in all of the stuff where you find titanium being used. It's not in hull structures, it's not in fuel tanks, it's not in anything else, because they didn't know how to weld it. So that is the only spot that you're going to see the use of titanium. That is the rover. It actually folded up. It's a working model. You can see pictures of it as it's being installed onto the LEM, okay? And it was in quadrant 1, and you count the quadrants counterclockwise on the LEM from the ladder counterclockwise around the machine. What it displaced was the big helium tank that was in there and the other oxygen tanks that were in there, and a spot where they had the extra batteries for the PLSSs were in that quadrant 1. They didn't get relocated, they just were removed because they were just on a stage. And of course, they were put up there on very tiny cables. You see them like little aircraft cables, like that would handle that anyway on the thing. But if you look in the pictures, there's large gantry crane cables that actually picked the rover up and moved it around on the set, and they actually leave the cables on the set. Where you see it in Apollo 17, right? The big cables. It has a single hook and 4 straps coming down with hooks on it to go right onto it. That's how they actually operated at Flagstaff to move it around and do the simulation on the thing. But anybody that says that the rover didn't fold, yes, it did. The trainers didn't need to fold. The ones they used for Santa Claus parades didn't need to fold. And probably most of those had gas motors and simple steering wheels as well. They might have put it on a joystick, but it was no more than little go-kart designs that they were doing that. And maybe the Shriners or whatever built the things. All of these misconceptions about it. Yes, they did build the machine. And if it worked as well as they thought it did, I mean, I could see Airstream taking out a contract to slap one of those on the roof of their Airstream trailers, because what would be more handy than go camping and have something like that to run around in?
Yeah, ideal.
And it folds up, it's lightweight, it's electric, it's everything.
Yeah, but if it folds up, you then got to use spanners, you've got to use connections to connect the wheels and the suspension type stuff.
Absolutely. And where are those tools?
Yeah, where are the tools?
And how are you going to put those things together? Even if you're hooking up the tie rod ends on the steering control, and let's say you just put it on a ball and socket and put it in, and you have a little cotter pin to just snap it into place so it doesn't fall out, because you don't want to do a screw down. You can do it with a cotter pin.
There's one big problem. How much are they going to sell these for once they manufactured them? Are they going to sell them for $100,000 a piece? Are they going to sell them for $1 million? 36 million? How much did it cost to manufacture these ones? Wasn't it 36 million a piece?
Yeah, well, the thing is those same people were hauling around golf carts instead.
Yeah, it comes from the same storeroom as they get the $10,000 loo seat.
If you're going to put together that much of a product and spend that much time and energy on it to make it super lightweight, everything is foldable, the seats folded down and everything to pack up, why wouldn't it be functional for many other commercial applications? Like when they built stuff for the war, that's why they built a Willis Jeep. They could drop it out of the back of an airplane on a parachute.
And they did.
And they did.
And that's where the inspiration for the Land Rover came from, the Willis Jeep.
Exactly.
On the control panel that you showed, the control panel on the Lunar Rover, was there any indication of how much battery strength that was left?
They had the voltmeters on there, and they had the temperature meters on there, and they had their what they called the little CAN buses that they could switch it. They could run on one battery.
Okay.
If it got hot, then they could switch it to the other. All of those dials are on there.
Yeah.
When you look at the lunar surface as NASA has projected this, that is nothing more than their lunar set that they're depicting, because they can't reproduce the pristine condition that the lunar surface would look like, the billions of years of cosmic dust that are there, the other material that comes down from impacts that are on those surface areas. And when you're on the Sea of Tranquility that has very little activity with impacts on there, the dust is going to build up. Even when you look at it in a telescope, you can see the crater, just the tiniest little crater rings are sitting there, and the rest has been filled in with material. Like you can see the fresh ones with the striations around them, the recent impacts on it. But the older ones have filled in. That's hundreds of feet deep.
All right, then why are the tracks all still there? Why are the Rover tracks still there? Why are the boot prints all still there? Why are the scruff marks still there on all of these LRO images that have been there for 50-something years? So that means that every time that dust levitates, it falls back down.
Because there is no LRO. There's just a camera shooting pictures off a plaster mold.
Don't say it's off the plaster mold. I think it's doing exactly what I did. All they're doing is going back in time, taking the originals right when they're taking off or whatever, right? And take a shot of that, and there you go. There's your LRO images. It's so simple.
That's off the set, which means if they claim there's pictures from an LRO showing the same thing, with the fine dust levitating with the sunlight, with the photoelectric charge every month, when the sunlight hits it, all of that stuff would be covered up. So if they're still showing it as a new LRO photograph, it means that there is no LRO orbiting the moon, because that's not where they're taking the images from. They're taking the images off of their own videos. So you don't need an LRO.
Right now on the internet, you're seeing a lot of film footage from Apollo that is being cleaned right up from the originals and being put out there, and it is so crisp and clear. It's just like it's a 4K image. Well, in fact, it really is a 4K image, what they've bumped it up to now. Yep. So if you do that and restore it and then start taking single shots when they're, supposedly taking off from inside the craft, there's every LRO picture you will ever need for every mission.
Exactly. Here, I'm going to share the screen. We'll just have a look at the lunar surface from a telescope.
Yeah.
Just wanted to show a little bit of difference. You can see a crater ring here, and you can still see the center of the impact on it. You can see the center of the impact on there. And you start looking at this. You can barely see the edge of that crater. Right there, it's all filled in. You can hardly see the edge of that crater. They're all filled in.
Oh, you know what would be really interesting? Take a photo from 55 years ago and let's compare it to this. And let's see how many craters are really filled in. That would bust it, because if there's empty craters 55 years ago, compare it to today, and those craters are filled in, then there's no way those tracks can be there, and there's no way that retro reflector could be reflecting anything. See, that would prove it.
Yeah, but what I'm saying is that these craters are hundreds of feet deep.
Oh, yeah.
And they're being literally filled in. Apollo 17 is right up in here, or right there, actually.
Yeah. And then Apollo 11 is further south. Go south from there.
Apollo 11's here.
Yeah, Apollo 11's there. That's correct. Yeah.
Apollo 11, and then 15's over here.
Yeah, 15's over there. 17 is halfway between the two. Apollo 17's there, correct, yes. And then Apollo 11 is left and south from there.
Down here.
Yeah, down there. That's right.
16's in about here.
That's right, yeah. You got 14 over on the left.
Apollo 12 is right there.
Yeah, because that big crater at the top is Copernicus crater.
Okay, and Apollo 14 is just underneath this guy here.
That's right, yeah, that's the one. Apollo 14 is where they did the golf shots, so we can go and look for golf balls there. There are plenty around.
Well, if we zoom in a little bit, maybe we'll see some.
Oh, see them, yes, of course we will.
Yeah, we're going to look at how the moon has changed over time here.
Oh, yeah. There we go.
This is Copernicus here in 1897.
Okay. Yep.
Here's Copernicus in 1970. And then here's Copernicus in 2017. Just between 1897 and 1970, where did this center stuff go from 1800s? I don't see it anywhere here.
Yeah, but that's raised. The center of that one is actually raised. Look at the shadow. It's not a depression. That's actually raised up. I'm looking at where it curls over the lip on the very left-hand side, right there. That's pretty close lined up. Man, did the details ever disappear. There must be a hell of a lot of rain and wind action going on there to wear down those mountains like that.
Oh, a lot of wind. And they've probably got floods as well.
You're saying that crater's, what, 60 miles across?
Yeah, 60 miles across and about 2 miles deep, or it was when it was photographed by Lunar Orbiter in 1966.
I'm looking at the amount of distortion between the two of them on the top half from the center up. Look at the difference on the inner part of the ring at the floor level going up.
Yeah, quite different.
It looks like it's washed away almost, like it's been rained on.
Then what's happened is that all of these ridges, you don't see them here anymore, so they must be all filled in with dust. This is all covered.
You'd have to have some pretty big impacts on there to kick dust around. Well, it's probably filled in the center of it as well, on the floor.
That top crater, see the top crater? That's visible in the next picture. Go to the same position in the next picture. There, that's the one.
That one.
That's the same crater by the look of it.
Then they're filled right in.
Yeah, it is.
Yeah, and the one directly below it isn't even there.
Which is why the diameter of the floor of the Copernicus crater appears different.
Then where is all this? It's gone.
Yeah. And this is only in how many years?
Well, this one here again, it says 1897. This one here is 1970.
You realize that you're talking about hundreds of thousands of feet of material missing that has changed? Like if that crater is supposed to be 2 miles deep?
Well, 2 miles deep when it was photographed in 1966 by the Lunar Orbiter. It's certainly a very different image.
It's quite different. That's a hell of a lot of material to be moved around. Things 2 miles feet deep and 60 miles across.
It is. There's a lot of material there, which is why there are so many fewer central peaks.
Yeah, if that's happened in that length of time, you show me how to keep a footprint pristine.
They all disappeared.
Okay, that's fine. They're all filled in. So this is what? Let's just say this is 65 years. It's been, what, 56 years almost since Apollo? So why are we still seeing tracks and boot prints when these craters are filled in?
And those are hundreds of feet deep.
That's the Warren Commission report version of Apollo. They're showing you what they want you to see, not what actually is there. Sorry, NASA, you haven't got it right.
They're not filled up. All these craters are empty, and yet here, like 60 years later, they're all filled in. Every single one of them. All the way down here, they're filled in.
Well, guess what? Those little craters you're talking about there, down there, just the little ones are more than a mile across.
These ones over here, you could still actually see them, but they're filled in, all of them. Look at this.
Yeah. And further down, there's a very distinct crater on the left-hand side, left picture. You can see the same crater virtually filled in the same position.
That's a lot of material.
Yeah, it is.
You're looking at a crater that's 60 miles across.
Yeah.
So even those little ones down at the bottom on the left-hand side are at least a mile across. They're not even visible. Those little ridges across there could be a half a mile or a mile high, and they're filled completely in. That's a tremendous amount.
Well, that electrostatic lift that appears every 14 days as the moon rotates produces a lot of material. It's got to go somewhere.
Yeah, well, like I said, Neil's footprints are an anomaly in itself. First of all, actually being there, and second of all, to continue to exist in a pristine state. That's just another one of those little stories that you just have to discount and just look at the reality. This is the reality.
Yeah, it is.
Well, there's something of interest that I would like to put out there.
On YouTube, I've discovered that there is a video. I'm not going to mention any names because I don't believe that's fair. But what had happened was, as we could see on the screen, there's a little reflection coming off of the ladder. And there's a hot spot there. And I believe that that's coming from a light that's behind the camera. Now, you have to first understand what a Vidicon tube is and how it functions. So what I'm going to do is I'm going to allow a clip to run so that you can understand how this tube works in the real world. And then I'm going to come back and I'm going to give my explanation of what is going on here in this video. So let's roll that clip.
It is known as the Vidicon, or, when constructed with a different photosensitive material, the Plumicon. The various parts of this camera tube are contained within an evacuated glass envelope of between 10 to 20 centimeters in length. At the front of the tube is a photosensitive signal plate, onto which the image to be transmitted is projected. For simplicity, we will show it the right way up. Situated at the other end is the electron gun, which directs an electron beam towards the signal plate. Around the tube is a focusing coil and 2 deflection coils which cause the electron beam to scan the signal plate. The signal plate then transforms the incident light into a picture signal that can be fed to the transmitter. Now that we've discussed briefly the construction of the tube, we will examine the various parts individually, to begin with the electron gun. A metal plate, the cathode, is positioned in the vacuum tube and heated by a filament. Due to this heating, many free-moving electrons are released from the surface of the plate. By chemically coating the surface, electron emission increases and a cloud of electrons forms around the cathode. Electrons are negatively charged. Therefore, another plate, the anode, is placed in front of it and made positive by means of a battery. The negative electrons are then attracted by the positive anode. They then flow from the anode to the positive pole of the battery, are returned to the cathode, and are again emitted. Thus, the cathode produces a continuous flow of electrons. Positioned between the cathode and anode is a Waynoldt cylinder, which enables the flow of electrons to be controlled. When the negative charge applied to the Waynoldt cylinder is increased, the cathode will emit fewer electrons. The speed of these electrons in the direction of the anode is, of course, very high, and by making a small aperture in the anode, a number of these electrons will be shot through it. In this way, an electron beam is produced, which is used to scan the signal plate. The electron beam is surrounded by a cylindrical electrode having, at the right, a fine metal mesh, and at the left, an electrical connection with the anode. As anode, cylinder, and mesh have the same potential, the velocity of the beam will not be affected. The tube will only function properly if the correct voltages are applied. The cathode may be at 0 volts, the Waynoldt cylinder at a low negative voltage, and the anode, including the cylinder and mesh, at a relatively high positive voltage. In contrast to the anode system, the voltage applied to the signal plate is low, and this causes the electrons to decelerate and to strike the plate with a very low velocity. For practical reasons, the shape of the electrode system is somewhat modified. Consider a magnetic field and in it a copper wire through which a current flows. A force is exerted on the electrons and the conductor is caused to move. This so-called Lorentz force is exerted on any electron that moves in a magnetic field, including one emitted by an electron gun. Without this field, it would continue in the same direction. But with a magnetic field, the Lorentz force deflects the electron upwards. The strength of the field can be increased to such an extent that the electron is forced into a circular path. The same force is exerted on electrons which move at an angle to the right. Here, the circular motion is combined with the initial movement to the right, resulting in a helical trajectory. In the camera tube, the gun is positioned along the axis of the magnetic field, and you will see that some of the electrons travel parallel to the lines of force. Other electrons will spread out and move along a helical path, passing through the axis of the field on completion of each loop. The velocity of the electrons is such that they all pass through the same point on the axis. Thus, the beam is focused. The stronger the magnetic field, the stronger will be the focusing effect. But for optimum focusing, the field strength should be such that the focal point occurs exactly at the signal plate, and this is achieved by controlling the current flowing in the focusing coil. Another coil assembly comprising deflection coils provides the scanning motion. If we first consider the coils shown here and apply a direct current to them, a magnetic field will be produced which deflects the electron beam to one side. If the direction of the current is then reversed, the beam will be deflected to the other side, and an alternating current will cause a rhythmic movement of the beam. In practice, a sawtooth current is applied. The beam then moves slowly to one side and returns quickly to the other. However, in order to scan the whole picture, we require not only horizontal deflection, but also vertical deflection, and to achieve this, a second set of coils is necessary. The magnetic field set up by these coils gives the electron beam a vertical movement, and by combining this horizontal and vertical deflection, the complete picture is scanned, 25 times per second. But what is the effect of this scanning process on the signal plate? And how is the picture signal obtained? As we have already seen, the signal plate is situated at the front of the camera tube. First, the inside face of the glass tube is coated with a thin film of tin oxide. This layer is so thin that light will pass through it. Moreover, tin oxide is a good electrical conductor containing many free electrons. A second layer, this time of a photoconductive material, is applied. In the Vidicon, this is usually of antimony trisulfide, whereas in the Plumbicon, it is of lead monoxide. The electron beam is directed towards the photoconductive layer. The transparent conducting film through which the light passes is connected to the positive pole of a battery. Let us first consider what happens when no light falls on the signal plate. The electron beam starts to scan the signal plate. In the dark, a photoconductor has a very high resistance, and therefore the electrons will not pass through it. The negative charge possessed by these electrons will repel the similarly charged electrons in the transparent film back to the battery. This action occurs over the complete area of the signal plate, leaving the film positively charged. 25 times per second, the electron beam scans the plate. But the negative charge repels the new stream of electrons, and these are then collected by the electrode system. This non-conducting signal plate behaves in a similar way to a charged capacitor. That is, it may be considered to comprise a number of extremely small capacitors. Each capacitor has an excess of negatively charged electrons, and at the right, a shortage of electrons, making it positive. In between is the photoconductive layer, which is, like any material, composed of atoms. The nuclei are shown in red, and the electrons in orbit around them in green. The photoconductivity is due to the electrons in the outer shell. These electrons are exposed to two forces. Firstly, the attraction of the positive nucleus, which binds the electrons to the atom, and secondly, the force exerted by the electric charge of the signal plate. the negative charge at the left and the positive at the right. The electric field created between these two charges exerts a force on the electrons, directed to the right. Consequently, all the electrons of the atom will move slightly to the right, but they will not break away from the nucleus. However, the situation changes considerably when light shines upon the signal plate. Light can be considered as a flow of energy quantums or photons. They penetrate the tin oxide and are absorbed by the photoconductive layer, just like the photon you now see passing the nucleus. Its energy sets free an electron which now moves to the positive layer. The following photons produce a similar effect. The vacancies left by the moving electrons are in turn occupied by electrons from neighboring atoms. This can be clearly seen from the diagram of one of the small charged capacitors. The last vacancy will be occupied by an electron deposited earlier by the electron beam. The electron deficiency at the left is regularly replenished by the passing electron beam. Simultaneously at the right, an equal number of electrons are returned to the battery. Poor light produces only a weak charge current, as can be seen from the meter. But as the light increases, the current becomes correspondingly stronger. In this way, the intensity of the light is translated into small current pulses, not only within these small capacitors, but throughout the signal plate. As we've seen, the scanning process divides the picture into a large number of horizontal lines. Let us then consider what happens in the signal plate along one of these lines. When the tube is switched on, the signal plate becomes charged. The light of the scene sets off the photoconduction process and discharge occurs. Where strong light is present, a large discharge takes place. But wherever the light intensity is less, a correspondingly lower discharge occurs. In this way, all the light impressions are stored and then transformed by the electron beam into charge impulses. This scanning process goes on repeatedly, line after line and picture after picture, producing an uninterrupted series of charge impulses which, due to their amplitude differences, carry all the picture information.
So, what has to be understood here is that a Vidicon tube works much differently than a CCD system that we see in cameras today. A totally different beast. So, let's go back to the film and have a look at the reflection on the ladder again. Now, what we're seeing here is a reflection that's coming from a light at the back of the camera. The light source is striking the ladder, and what's happening, because if we look down below, you can see that the Vidicon tube is being saturated, which means that one of the plates in the tube is being saturated. The circuitry is trying to compensate this. It can't do a very good job because of the fact that the photosensitive material is also being saturated, as we have seen 3/4 of the way through the video when that section is playing. You will also notice that the reflection of the light on the ladder is actually being reflected back into the lens, and this is being picked up by the Vidicon tube because it's oversaturated. Now we turn to the astronaut. We can also see his backpack. Because the Vidicon tube is oversaturated, it actually seems to appear to drag the reflection from the ladder along with him. And we can also see this at the very top of the astronaut's helmet. This little reflection that seems to be out in the middle of nowhere is caused because of that tube being oversaturated, and the astronaut, on the top of the astronaut's helmet, we can also see that the light is striking the helmet, and the reflection from the lens
is causing that light to also drag along with the astronaut. This is all due to the fact that the Vidicon tube is oversaturated. That's all it is, friends. The Vidicon tube is oversaturated, and the circuitry cannot compensate for this. It's nothing more, nothing less. Nothing less. Nothing less. Nothing less.